I would like to thank Alexey Nikolaevich Karapetyan's and all his team for organizing this wonderful conference in such a difficult time. So I'm going to talk about operator error estimates for homogenization of higher order hyperbolic equations. Let us start with the statement of the problem. By gamma, we denote a lattice in AD. Omega is the cell of this lattice. Gamma tilde is the dual lattice, and omega tilde is the central Brillouin zone of the dual lattice. For instance, if gamma is the cubic lattice ZD, then omega is the unit cube. Gamma tilde is also cubic lattice 2 pi z to the power d, and omega tilde is this cube, minus pi to the power d. Now our main object, it is operator A epsilon. Epsilon is a small positive parameter. It's a self-adjoint differential operator acting in L2 AD Cn. It's L2 space of Cn valued functions in AD. And we assume that A epsilon is written in such factorized form. It is also written on the whiteboard. The matrix in the middle, G epsilon of x, is of size m by m. And we use such notation. G with index epsilon of x is equal to G of x over epsilon. It is assumed that this matrix valued function G is periodic with respect to the lattice gamma, bounded, and uniformly positive definite. In general, G of x is a Hermitian matrix with complex entries. And we don't need any smoothness assumptions on G. Next, this operator B of D is a homogeneous differential operator, matrix differential operator of order P. Here all derivatives are of order P. B alpha are constant matrices of size m by n. And we suppose that P is greater or equal than 2. So the order of the operator is at least 4 or 6, etc. The matrices B alpha are of size m by n, and it is assumed that m is greater or equal than n, and the symbol B of xi has maximal rank. The rank of B of xi is equal to n for any non-zero vector xi. It's an ellipticity condition. The precise definition of the operator is given in terms of the corresponding quadratic form defined on the Sobolev space HP. Under our assumptions, this form satisfies such two-sided estimates, and it means that our operator is strongly elliptic. In the case where P is equal to 2, such operators arise in the theory of elastic plates. Our problem is to study the behavior of the following operator valued functions of A epsilon. The operator cosine of the square root of A epsilon multiplied by tau. Tau is a real valued parameter, it's time. And the corresponding sign multiplied by A epsilon 2 minus 1/2. We study the behavior of these operators for small epsilon and arbitrary tau. We will formulate the results in the operator terms, but of course we can apply them to study the behavior of the solution U epsilon of the following Cauchy problem. Here we have a hyperbolic equation involving A epsilon and initial conditions. It's well known that the solution of such Cauchy problem admits the following representation, which involves exactly these operator functions. We show that in some sense these operator valued functions of A epsilon behave as the corresponding operator valued functions of the operator A naught. Here A naught is the effective operator with constant coefficients. G naught is the constant positive definite matrix called the effective matrix. And we recall the definition of G naught. The definition, of course, is well known, but it is non-trivial. To define the effective matrix, we first consider the auxiliary boundary value problem, which is called the cell problem. Let lambda of x be the matrix valued gamma periodic solution of this equation. So we consider this elliptic equation on the cell omega with periodic boundary conditions. And the solution is fixed by this condition that the mean value of lambda is 0. Next, we define the matrix valued function G tilde of x in terms of lambda by such relation. And the mean value of this G tilde is G naught. It turns out that the matrix G naught is always positive definite. Now it's convenient to give a short survey of the known results. The case of the second order operators, A epsilon, is well studied. In 2001, in our joint paper with Mikhail Solomonovich Birman, it was proved that the resolvent of A epsilon converges to the resolvent of A naught in the L2 operator norm. And the norm of the difference satisfies sharp order estimate 2. And this was obtained by the new approach, the operator theoretic approach. Later, a similar result, estimate 3, was obtained for the parabolic semigroup. Again, for second order operator. Also, more accurate approximations in the L2 operator norm, as well as in the energy norm, the norm of operators acting from L2 to H1 for the resolvent and for the semigroup have been obtained. And such estimates, 2 and 3, are called operator error estimates in homogenization theory. A different approach, the so-called shift method to operator error estimates, was suggested by Vasily Vasilievich Zhikov and Svetlana Evgenievna Pastukhova. They published a big series of papers and a big survey in Russian mathematical surveys. Now let us discuss the situation with the homogenization of Schrödinger type equations and hyperbolic equations. The situation differs from elliptic and parabolic cases. Our last joint paper with Mikhail Solomonovich Birman in 2008 was devoted to such non-stationary homogenization problems. We studied this exponential and this cosine. And it turned out that it is impossible to prove error estimates in the L2 operator norm. We have to change the type of the norm. You see, for exponential, the norm is from H3 to L2. Then we have order sharp estimate. And for cosine, the norm is from H2 to L2. And also note that on the right, we have this factor, 1 plus modulus of tau, which grows for large time. Yulia Mishkova obtained a similar result, estimate 6, for this operator function with sine. Now we proceed to the results for the higher order operators. The operator theoretic approach was applied to the higher order operators in the works by Nikolai Veniaminov and in our joint paper with Andrei Kukushkin. Andrei Kukushkin. It's another Kukushkin, my former student, Andrei Kukushkin. So this estimate is the same as for the second order operators, but now A epsilon is a higher order of order 2p, estimate 7. Svetlana Pastukhova obtained a similar result using the shift method. Also, approximations for the resolvent in the energy norm were found. And recently, more accurate approximations for the resolvent in the L2 operator norm were obtained independently by Vladimir Slosh and myself, and by Svetlana Pastukhova, by different methods. In particular, in these papers, Slosh, Suslina, and Pastukhova, it was found out that in the scalar real case, we have improvement, estimate 8. What does it mean, scalar real case? The coefficients are real valued, and n equals 1. So the operator acts on scalar functions, not on vector functions. In this case, we have a better result than estimate 7. Estimate of order epsilon squared without any corrector. And it was a new effect. We don't have such effect for second order operators. Next, in my recent work with Alyona Miloslova, a similar result was obtained for the semigroup for higher order operator, and also approximation for the semigroup in the energy norm was obtained. And again, we have such effect. In the scalar real case, estimate is improved. For fixed time, it's estimate of order epsilon squared. And finally, in my recent work, this exponential was studied for higher order operators, and estimate 11 was obtained. Here, the norm is from H to P plus 1 to L2. If we take such norm, then we have sharp order estimate, epsilon here. And again, improvement for the scalar real case. Now we formulate our main results. Main result is theorem 1. Let A epsilon be the operator of order 2p, defined above. Then we have such error estimates. For cosine, the norm is from HP plus 1 to L2. Then we obtained sharp order estimate, the first power of epsilon. For this operator function, the norm is from H1 to L2. So the type of the norm doesn't depend on P. This is because we have this a epsilon to minus 1/2 in front of the operator sign. Okay. And theorem 2 concerns the scalar real case. If n equals 1, so the operator acts on scalar functions, and the matrix G of x and the matrices B alpha have real entries. We consider scalar real case. Then we have improvement. For fixed time, estimates of order epsilon squared, inappropriate operator norms. Here are the results. Also, we can obtain interpolational results, the so-called intermediate estimates. For example, under the assumptions of theorem 1, we can take the obvious estimate, the difference of cosines in the L2 operator norm obviously does not exceed 2. And we can interpolate between estimate 17 and estimate 13. It's the result of theorem 1. And then we obtain such intermediate estimate of order epsilon to the power s divided by p plus 1 for any s between 0 and p plus 1. Of course, other results also have interpolational corollaries, but now I don't have time to formulate all interpolational results. Now let us briefly discuss the method. It's operator theoretic method. It is based on the scaling transformation, the Flaquet-Bloch theory, and the analytic perturbation theory. And I will explain the method for the operator cosine. So we ask a question. For what minimal s the estimate 18 holds? It's estimate in the norm from HS to L2, and we wish to have the first power of epsilon on the right. What s should we take? First, let us denote by h0 minus Laplacian. And it's convenient to consider estimate 19 instead of 18. They are equivalent. We take this difference of operator cosines and multiply by the smoothing operator, h0 plus identity to the power minus s over 2, and then we take the norm in L2. Estimates are equivalent. Next, we apply the scaling transformation, and we see that estimate 19 is equivalent to estimate 20. Here, the operator A is this one. It does not depend on epsilon. It's the operator with the matrix G of x. But here we have tau divided by epsilon to the power p due to the scaling. The smoothing operator takes this form after the scaling. Next step is the Flaquet-Bloch theory. So the operator A with the matrix G of x has periodic coefficients. And then this operator A is unitarily equivalent to the direct integral of operators A of k. The parameter k is called the quasi-momentum. K belongs to omega tilde. And the operators A of k act on the cell, not in AD, but in L2 omega Cn. A of k is given by this differential expression. So with respect to the parameter k, it's a polynomial of order 2p. And we consider this A of k on omega with periodic boundary conditions. the corresponding unitary operator, A is unitarily equivalent to the direct integral. The corresponding unitary operator is the Gelfand transform, but now I do not write it down. It's important that it is unitary. And similarly, we can write down direct integral expansions for the effective operator A naught and for H naught minus Laplacian. And applying these direct integrals, we see that the required estimate 20 is equivalent to estimate 21. In fact, it's the same estimate, but for operators depending on quasi-momentum k. And the norm here is an L2 omega. And we have to prove this estimate for almost every k in omega tilde. The last reduction is related to orthogonal projection of the space L2 omega Cn onto the subspace Gothic n. It's the subspace of constants, constant vector valued functions. It is n-dimensional subspace. By P, we denote this projection. It's simply a region over the cell. And it's easily seen that the required estimate 21 is equivalent to estimate 22. What happens? We multiply the difference of operator cosines by the projection P onto constants. It can be easily shown that the remaining term with P orthogonal goes to error. So it suffices to consider this operator with P. If we have projection onto constants, then the operators with constant coefficients act simply as multiplication by their symbols. So before we have here A naught of k, differential operator, and now S of k, it's the symbol of the effective operator. Here we have the smoothing operator, and now it turns simply in this smoothing factor, depending on epsilon and k. So this is the last reduction. And the main part of study is the study of the operator family A of k by means of the analytic perturbation theory. A of k is an elliptic operator in a bounded domain. So it has discrete spectrum. Its resolvent is compact. And it depends on k analytically. We can apply analytic perturbation theory. We consider A of 0 as an unperturbed operator and A of k for sufficiently small k as a perturbed one. The kernel of the unperturbed operator is exactly Gothic n defined above, the subspace of constants. So we have n-dimensional kernel of the unperturbed operator. The spectrum of the unperturbed operator looks like this. The point 0, lambda not equal to 0, is eigenvalue of multiplicity n. Then we have other eigenvalues. Then, for sufficiently small k, the modulus of k less or equal than some t naught, the spectrum of A of k looks like this. On the interval from 0 to delta, we have exactly n eigenvalues. Lambda 1, depending on k, lambda n. And we have nothing on the interval delta 3 delta. This interval is free of the spectrum. This is the spectrum, a part of the spectrum of the perturbed operator. We control, of course, we control this delta and denote explicitly. And it turns out that for our problem, only this part of the spectrum is important. And this part goes to error. Next, we write k as t times theta. T is the modulus of k. It's our main one-dimensional parameter. And theta is the unit vector, the direction of k. And we will write a of t and theta instead of a of k. And this operator family, a of t theta, is studied by means of the analytic perturbation theory with respect to the one-dimensional parameter t. But all the estimates should be uniform in theta. By the Cator-Ehrlich theorem, for t less or equal than t naught, there exist real analytic branches of the eigenvalues lambda L and eigenvectors phi L of our operator family. They are analytic in T, but they depend also on theta. And the set of phi L's forms an orthonormal basis in the eigenspace corresponding to this part of the spectrum, lying the first 10 eigenvalues. Then, for small t, we can write down power series expansions for analytic eigenvalues and eigenvectors. The expansion for lambda L starts with term of order t to the power 2p. The coefficient gamma L is strictly positive, separated from 0. Expansion for phi L starts with some embryo omega L, and the set of these embryos is an orthonormal basis in the subspace of constants. And these coefficients are very important. They are called threshold characteristics of our operator family at the bottom of the spectrum, the coefficients gamma L and the vectors omega L. S of theta, we consider S of theta. In fact, it is the symbol of the effective operator on vector theta. It is called the spectral germ of our operator family. And it turns out that these coefficients gamma L are eigenvalues, and the embryos omega L are eigenvectors of the spectral germ. Next, we need the so-called threshold approximations. This proposition 2 was proved in our joint work with Andrei Kukushkin. By f of t theta, we denote the spectral projection of our operator for this interval, 0 delta. Then, this projection is approximated by p, projection onto constants. The error is of order t for small t. And our operator multiplied by the spectral projection f is approximated in terms of the spectral germ. Here, the error is of order t to the power 2p plus 1. And we also deduce estimate 27 approximation for the square root of a multiplied by f. And now we can easily prove theorem 1. Proof of this estimate 13, it's the result of theorem 1. Using the, of course, using the reductions described above. Instead of cosines, let us consider the corresponding exponential. So we take this difference of the exponentials, multiply by projection p. Then we have such representation, 3 terms. The first 2 terms involve f minus p. And we have estimate this threshold approximation for f minus p. The third term, this integral term, involves square root of a f minus t to the power p square root of sp. And for this operator, we have this threshold approximation. So using such representation and this proposition, we immediately obtain estimate 28. The right-hand side depends on t and tau. Now recall that we have to replace tau by tau divided by epsilon to the power p using our reductions. And also we have to multiply this norm by the smoothing factor. And then we immediately arrive at the required estimate. So this completes the proof of the estimate for the operator cosine. The second result for the operator sine is proved similarly. And finally, about theorem 2. Theorem 2 was improvement in the scalar real case. It turns out that in the scalar real case, we have proposition 3, which was obtained in our recent paper with Vladimir Slouch. These threshold approximations are better. They are improved compared with proposition, the previous proposition. So applying these improved threshold approximations, we can obtain the improved results, theorem 2. Well, some references, and thank you very much.
Thank you for this presentation. Any questions?
Yes. I have a question. You brought some estimates norms from A2 to A2, and some estimates from H spaces, H2 to A2. What estimates more general?
The estimates from L2 to L2 are obtained for the resolvent and for the parabolic semigroup. But for exponential, e to the power minus I, a epsilon tau, and for this operator cosines, operator sines, it is impossible to prove error estimates in the L2 operator norm. So we have to change the type of the norm. We take the norm from some appropriate HS space, the Sobolev space, to L2. In fact, there are results for the second order operators. Our results with Mark Dorodny, we show that all the results are sharp. If we wish to have epsilon on the right, epsilon is the best. Then we should take exactly these norms. For example, for exponential from H3 to L2, for cosine from H2 to L2, the results are sharp with respect to the norm type. And also, the results are sharp with respect to dependence on tau. We have the growing factor on the right-hand side, 1 plus modulus of tau. This is also sharp in the general case. However, in the scalar real case, this can be improved. In the general case, the results are sharp.
Any other question? Yes.
Are there any spectral consequences of these estimates?
Spectral, I don't think so, because the spectrum of the effective operator is operator with constant coefficients. The spectrum is the whole semi-axis. And of course, the spectrum of A epsilon converges to the spectrum of A naught. But for A epsilon, we have bands and gaps, and for the limit operator for A naught, we don't have bands and gaps, just the continuous spectrum, semi-axis. So it's not so interesting.
Okay, let's turn to the speaker again.